Hi guys, it's Matt Denicky with Denicky Racing Technologies. Some of you might have seen on Facebook posts about my YZ400 project, and I figured I would do an introductory video walking through how we got to this point so far. So sit back, enjoy. Hopefully this isn't too boring. I'm definitely an engineer and not a YouTuber, so this will be a little bit of a learning curve. But here we go. So first off, the scope of the project. And what did I want to do? I wanted to build an open class MX bike with more modern bells and whistles, modern porting, pipe design, something that uses the up-to-date technology we have nowadays to come up with a good design that is well-rounded and preferably fast. Now, I've spent the majority of my riding time on 252 strokes and I'm very comfortable on them. I very much like the power curve of them. So I didn't really want to have to relearn my riding style. And I wanted something that has kind of that broad but, fast revving 250 feel, but obviously more power and not so much like the old 500s are. Um, I also wanted no frame mods. I'm a great machinist. I'm not a great welder, and I didn't trust myself to have to, start hacking up a frame and trust that it's going to hold together. So no frame mods allowed, and I wanted it to be, very fast, very exciting, but I do still want it to be somewhat rideable. Now, something with 70, 80 horsepower might be difficult to be rideable no matter what you do to it, but we're going to see how this goes. Now, so back to the 500s. Um, the old style 500 power curve is very mid-range oriented. The KX 500 a little less so than the CR 500, but they hit very hard in the middle and mostly sign off. Um, there are ways to stretch that out, but at the end of the day, the CR especially is built on pretty old technology. It doesn't have a power valve. It's got single bridged exhaust port, pretty old transfer design. So while it's a legend, it's there's room for improvement, and the same goes for the KX. The KX is largely based on the KX 250 bottom end with a massive cylinder on it. So there's definitely a little bit of room for improvement there. Um, Now, a lot of people have brought up BRC before. I think Riley's a great dude. He's very smart. They have an excellent product. But me being an engineer, I couldn't settle. I couldn't settle on taking somebody else's work and improving it. I wanted to start with a blank canvas. And when I say improve it, that's not to say that there's massive improvements to be made with the BRC kit. They do a great job, but it's a production motorcycle. So, they make it kind of in the same vein that Yamaha makes the YZ250. It's a very well engineered starting point, and you can change it to be better at woods. You can change it to be better at MX. You can change it to be better at desert. But as a overall starting point, it's a great bike. Don't get me wrong. Um, Even still, with the BRC as well, like I don't remember off the top of my head where it makes peak power, but I think it's a little bit lower than the 8,500 RPM goal that I was hoping for. So, um, well, yeah, it probably would have been cheaper for me at this point to do it that way, and it certainly would have been a lot faster. I wanted to start with a blank canvas. I thought it would be, a worthy engineering exercise. So, yeah. Now, Project Origin, um, you can see in the picture on the left somewhat of a mock-up of where things started. Just like, will it fit in frame? The cylinder. So the snowmobile's off. The cylinder is off a snowmobile. The idea for the project started around 2018 from a customer of mine named Jonathan, who I met in the early days of Apex Racing, the head company I started. And I sold him a cylinder head, and I ended up doing a bunch of machining for some road race bike parts for him. And at the time, BRC was pretty early in their run of KTM 500 kits. We were talking about how cool it would be for there to be something similar for the YZ. Now, we came to the conclusion that a snowmobile cylinder would be a good starting point, since he sent me a used one and a damaged set of cases for free. And he basically just said I can pay him back by making it happen one day. So big thanks to Jonathan. This project probably wouldn't have started if it wasn't for that conversation. I definitely have to thank him for that. Now, fast forward to my time at Electron. I was very homesick being in Texas, and my wife was traveling a lot for work. So I spent a lot of time writing two-stroke simulation programs after work. And these programs lay the groundwork for the theoretical side of the project. You can see one of my spreadsheets on the right there. That's kind of just a basic info page, but it goes a lot more in depth than that. Moving on, after about a year of programming, I started hitting some dead ends with my engine programs. The goal of any good software is to be able to accurately model and predict performance before any physical components of the engine are ever made, and to provide insights on how to go about making changes or improvements after you validate the model against the first prototype. My programs work well for getting performance indicators for individual components like the head, the ports, etc. But I was having a hard time fully integrating the unsteady gas dynamics calculations into the VBA Excel architecture I had started with, and was getting results that I wasn't really happy with. They could get me ballpark numbers, but I wanted fairly specific numbers for this math. If I was going to take the time to make this project a reality, I wanted something that I knew would work, and I just needed to pony up and buy a proven software. This is where I met Niels von Niekerk and Wayne Wobbly Wright. I did a ton of research into the pros and cons of the different software packages available, and EngineMod 2T was the clear front runner. Niels has been continuously doing academic level research and updating this program since the 80s, and it's extraordinarily powerful for something that can run on a laptop. Normally, to get a full CFD, you would need a mainframe computer, the type of stuff that would take up a whole room, not something that you could have in your home. So coming into this project, I was already very well versed in engine design and tuning from my years at Apex and then Electron, and just general two-stroke knowledge. But using this software really opened my eyes into how much more there is to know. The finer details of how the program works is well beyond the scope of this video, but if you all want me to do another video on the software, definitely drop a comment. I can give a little bit more of a background to how the program works, but it's pretty mind-boggling stuff. After about a month of being a hermit and learning the ins and outs of how the software worked by walking myself through the testing I had done in real life on my 250 over the years, I was ready to start the 400 in earnest. Wainwright was extremely helpful during this stage in explaining some of the less obvious details that come with experience and fixing some of my mistakes in the model that were skewing my results. This saved me a lot of time and a lot of effort. So big thanks to Wayne for that. Just like I learned in college, garbage in equals garbage out, and you need to know what knobs, or in this case, engine parameters, to turn to get the results you want. Now, engine theory can only get you so far, and the most effective way of using the software is knowing its limitations and letting it help you narrow down the combinations of things you want to test in real life. The biggest question mark with any program is that it's not a CFD model. As I said earlier, they need supercomputers to run. And without CFD, the scavenging phase is a little bit of a question mark. Scavenging is when all the ports are open and fresh charge is replacing the burnt charge in the cylinder. Now, while the concept is simple, the math behind it is very complex, and for our purposes, some simplifications need to be made. This makes it so that I get to basically pick between good, medium, and bad scavenging, essentially, But there's not a foolproof way of knowing how different port angles will act without a combination of testing and experience. This also puts limitations on how big you can make the exhaust port without fresh charge short circuiting into the exhaust ahead of the burnt charge that it needs to be replacing. There are also some assumptions that need to be made on temperature boundary conditions, combustion parameters, and the dimensional accuracy of my measurements that were used to make the model. So I went ahead and came up with the following sets of parts I wanted to test. 4 cylinders ranging from a cleaned up stock MXE800 HO cylinder, one with slight mods, moderate mods, and extreme mods. 3 cylinder heads, all with the same squish clearance and bandwidth. 2 are 14:1 with different chamber shapes, and 1 is 13:1 in case I need to go lower in compression. Ignition timing. The cases are designed to allow static timing to be adjusted from 0 degrees to 10 degrees more advanced than a normal YZ250 instead of plus or minus 5 on the normal YZ cases. Simulation results showed that +8 was the best compromise, but eventually I will need to transition to a programmable unit to optimize past that. For the pipe, I designed a custom pipe that is in the power curve pictured, but I also designed a separate exhaust flange that accepts the OEM pipe or other aftermarket YZ250 pipes. The simulation still shows that the OEM YZ pipe should make about 78 crank horsepower, which is more than enough for initial testing, and it's good to have as a backup, especially if you're making custom pipes. They're quite expensive, and motocross bikes are known to hit the ground and dent pipes, so it's good to be able to just buy something off the shelf and still have a usable bike. I also plan on measuring all of the other aftermarket pipes that I have to see if any of them would be a better alternative. This will likely be one of my next videos. Case volume. I intentionally designed the crankcase area with extra case volume to lower the crankcase compression ratio. This follows more modern theory that pipe suction does more for scavenging than case pressure. However, my simulation showed better results with slightly less volume. My judgment as to why is that even the custom pipe I designed is proportionally smaller than the more ideal pipes that the principle was developed around with 125 GP bikes. To be able to test both, I had made a set of stuffers that encapsulate the crank area and take up the extra volume. And they have the added benefit of thermally insulating the fresh charge in the cases, which is a good thing. For carbs, I have 2 different electrons to try. One is an off-the-shelf Big Air Pro that I know will work well. The other is a custom one I made with a different bore shape and a separate pilot circuit. That'll be interesting to try, but I'm probably going to end up sticking just with the off-the-shelf one because they work so well. For reeds, I've been working with Boysen on a dedicated set of reeds for this build, similar to the YZ250 prototype ones that I've been testing for them with a lot of success. I'll probably do another video walking through how they work as well. And if the 400 versions of those prototype reeds don't work as well, I can always fall back on their standard MXC reeds. Next, the power valve is diaphragm operated. And instead of using a spring or a fixed jet to control its timing, I used an adjustable jet screw to make its timing variable and externally adjustable, which is really nice. That'll play a big part in tuning the power delivery to what we need. And eventually I might convert that power valve to be servo operated for even more control after that. Let's see. Now, some final parameters for just like the general architecture of the engine, the stuff that would be on a spec sheet on a website or whatever. It's a 82 by 75.7 stroke. That's the stock Bourne stroke for an MXE800, which gives 399 cc's. The rod length is actually from a Sea-Doo jet ski, and it's 140 millimeters. Compression ratio, we're going to start with 13 or 14:1, depending on which one works better. As mentioned earlier, I have variable crankcase compression ratio ranging from 1.4 to 1.45, depending on if they're on the stuffers or not. Fueled by Electron Pro Series 39 millimeters. Cylinders are modified MXZ800 ones. Target power is 80 horsepower at 8,500 RPM. The standard YZ parts will be transmission, clutch, water pump, stator, swing arm bushings. I'm probably missing a few minor ones here and there. And then custom parts, the cylinder head obviously, power valve, crank, primary drive gears, which we'll get into in a minute, cases, ignition cover, and the final exhaust. Next, we're on to mechanical design. A lot of reverse engineering to do. Had to reverse engineer all the off-the-shelf components that I was planning on using. This included the cylinder, piston, rod, stator flywheel, transmission, clutch, water pump. And I also had to very, very accurately measure all the bearing spacings from the pockets in the original YZ cases. This is really, really important to get right, or otherwise there'll be issues down the road. This was very time consuming. I did not have a 3D scanner at the time, and I had to rely on a lot of hand measurements with various measuring tools, and had to get creative for a lot of it. Getting an accurate model of the cylinder was particularly challenging, with the ports being complex shapes. I had for many of them to make wire frames out of them with little pieces of wire, and then trace those onto paper and take a picture of the trace, and fit a spline to it in CAD, and then construct them that way. Now, since I won't be casting an exact replica of these cylinders, this was more of an academic exercise, and I would definitely do it differently in the future. Would not do it that way again. Now, for critical dimensions such as the transmission bearing locations, I had to make do with Electron CNC mill with a probe as a poor man's CMM, or coordinate measuring machine. This was even more time consuming and ate up most of my weekends for a few months or a few weeks. It was very time consuming. I then modeled the transmission bearings floating in space, but with the spacing locked at first so that I could adjust their orientation relative to the crank and the swing arm pivot. This was going to be important later. Next, I designed the crank webs around the big end pin and the section of cases that surrounds the crank based off my engine mod numbers. Once this is done, I used dimensions from my floating bearings to make a parametric sketch that allowed me to move the gearbox around. I needed to find an orientation that fulfilled a few key constraints. First, the countershaft sprocket needed to remain in the same place relative to the swing arm pivot and the engine mounts. This is important for the bike to handle properly. I can do that in another video, but essentially the swing arm pivot, countershaft sprocket, and rear axle make a triangle, and the way that triangle is angled controls how much the bike has anti-squat properties under power. And it's pretty important. So I didn't want to change any of that. I like the way the bike handles fine. There needed to be room to accommodate the larger diameter crank webs while maintaining clearance for the transmission gears, engine mounts, while leaving enough room for case thickness and water passages. The distance from the crank to the clutch basket needed to be increased for clearance, but could only be increased in discrete intervals in order to line up with both the tooth counts of the larger primary gear, which I'll get into later. There needed to be room to fit the cases in the frames such that the cylinder and pipe would clear everything with no frame modifications. This was tricky because obviously there's the Y for the pipe, and then the ignition coils right over that, and various other parts of the frame and gas tank and radiators are in the way, and just makes for a all-around challenge. I did this by importing a picture of the bike into CAD and scaling it to size because I don't have a 3D scan of the whole bike, or at least I didn't at the time, so that was all I could really do. All of these constraints ended up being quite the balancing act to juggle, and I spent the better part of a month trying different orientations until I got it all to fit. I ended up having to get creative and made the clutch stacked a little higher than the crank so that it was no longer in line with the countershaft and crank. This helped me maintain a compact design and minimize wasted space. As mentioned earlier, the primary gearing had to be changed to accommodate the larger crank. However, this gave us a few added benefits. First, this made the primary drive ratio taller, or a smaller ratio, meaning for the same engine speed, the bike would be going faster. Due to the way power and torque are transmitted through gears, this means that while the gears are spinning faster, for the same amount of power, they're under less torque and load. This will help improve gearbox and clutch life, while reducing this ratio by reducing this ratio from 3 to 1 to 2.25 to 1. The gearbox torque only increases by 25%, despite the engine torque increasing by 67%. If the final gearing was left alone, this gearing would likely feel way too tall, with third gear feeling like fifth gear on a 250, which is just way too much. So by reducing the front sprocket to 13 teeth, third on the 400 would feel like fourth on the 250, which I think would be pretty appropriate for the amount of torque this bike has. So basically, instead of getting first through fifth, you'd have a second through a theoretical sixth if you were on a normal YZ, if that makes sense. But to get the speed fully back to what it would be with YZ250 gearing, you would essentially have to run 1254 sprockets, which aren't available. The closest you can get would be a 1252, I believe, which would be pretty close. Second, this required changing the gearing for the water pump as well. It'll now spin 25% faster. This was done to make sure that gear cleared the larger primary gear, because there's two of them stacked on top of each other, which isn't a bad thing. It'll help deal with the added heat of the larger engine. So again, not a bad thing at all. Once the spacing was figured out, it was just a matter of designing the cases around the rest of the components. This is obviously easier said than done and took several months of slow progress. Structural ribbing from the original YZ cases was mimicked, and the OEM style oil passages were also maintained, further adding complexity but ensuring long-term reliability. The inner clutch cover also needed to be designed, as well as the ignition cover. The OEM clutch cover from the YZ and water pump covers will be used, but had to be reverse engineered for the model. The cases were also designed so that I could modify them later to accept a custom cylinder if I decide to have one cast. The main limitation of the Ski-Doo cylinders being that the bore spacing makes the transfer ducts, a little less radiused than they should ideally be, and that would be something I'd want to improve on eventually. Once the CAD models were near completion, it was time to validate fitment. I bought a 3D printer and had to section the model into pieces to print, since it was too big for any reasonably priced printer. By staggering the split points, I was able to bolt the parts together while the super glue dried, and got pretty good alignment between the pieces. The plastic cases were then bolted in the bike to see if there were any fitment issues. Thankfully, only a few minor tweaks were needed, which were then passed on to the CAD model. This also gave the opportunity to test fitment on some of the internal components, though these need to be taken with a grain of salt, since the 3D print is not as accurate as a machine part. Again, only a few tweaks were needed, and my diligence during the design phase paid off. I was also able to use this model to design the exhaust and intake manifolds. Again, since I didn't have a full 3D scan of the bike, I needed to use some educated guesswork to get everything to line up right, using 3D printed manifolds bolted to the plastic engine. I ended up designing, printing, and test fitting something like 5 exhaust manifolds and 15 intake manifolds. It's definitely a big pain, and I wish I had a 3D scanner back then like I do now. Next, on to porting and cylinder prep. As I mentioned earlier, one of the cylinders was gifted to me. It was a usable conditioned HO cylinder, high output cylinder. I knew that I'd want a few cylinders to play with, since I wanted to plate after porting anyway. I could get relatively cheap beat up ones. Furthermore, since I could port them however I wanted, I could start with non-high output MXZ cylinders and turn them into high output ones, or go further, which is what I ended up doing. Um, as you can see in some of the pictures, some of them were in pretty rough shape. I planned out how I wanted to stage my testing of different port geometries. The high output cylinder I left alone to be the baseline. The others would go progressively more aggressive. The 3 ported cylinders I used, the same port timings on all the each of the ports, but varied the widths and angles to test different properties of them. The first cylinder had a heavily reworked intake port and widened auxiliary exhaust ports with some small duct modifications and general cleaning up. The second cylinder had the addition of a heavily reworked center exhaust port, and then the third cylinder has another addition of the transfer ports being widened and re-aimed for the rearward. After porting, the 3 cylinders were sent off to Gary at Millennium, who did a fantastic job repairing all of the damage and replating the cylinders to like new condition. I cannot speak highly enough of his quality and attention to detail. We also worked together to decide on the optimal piston clearance for this application. And Gary's such a wealth of knowledge. It was a pleasure picking his brain and working with him on this. And I can't thank him enough. Next, it was time to manufacture all the custom parts. It was around this time that I decided it was time to leave Electron and start making my way back to Virginia. While I had a great experience at Electron, living in Texas so far from my friends and family was really hard on my mental health, and I needed to make a change. The project got put on hold for a while I was looking for jobs and moving. Earlier this year, my wife and I were able to make the move back, and I finally settled into a normal engineering job near where I used to live in Virginia. This made it possible for me to continue funding the project, and it also opened up the availability to use some of my old machine shop's equipments at Apex Racing Heads in exchange for some engineering help after hours. They've been great at supporting me since I sold the company several years ago, and I still try to help them out as much as I can on the side. They're another company I definitely recommend supporting, and they make great products that I just so happen to design. Some of the parts were not well suited towards the equipment at Apex, and for them I had to find companies to outsource to, such as the crank and the gears, for example. This proved to be difficult, as finding companies that are willing to do one-off parts without promise for a big contract in the future are pretty hard to find. Over the course of several months of searching and talking to my contacts in the industry, I narrowed down my search and decided on tolerances for every dimension of every part. Got the parts quoted, ordered, and slowly they've been coming in, which has been very exciting. Having finally completed the cases, the last piece is to have the crank assembled and balanced by Brian at Mototech, who's been a huge part of the project as well. He's helped me source parts, taken dimensions of things while I had my stuff in storage, and various other random tasks that I didn't have the resources to do when I was between Texas and Virginia. He does top-notch work and is one of my go-to resources in the industry. So next steps. I also decided that with all the time, effort, and resources I put into this project, it deserved to have a new bike to put this engine in. And so I went and bought one earlier this year. I have my wife to thank for that. I've told myself for years that I wouldn't buy a brand new bike, but she pushed me to take the step and do it and reward myself for all my hard work. So thank you so much, Catherine. Most wives are not nearly as cool as you, pushing me to buy more bikes when I already have other bikes, which is pretty cool. So that brings us to where we are now. I still need to do the final inspections on all the custom parts and make sure nothing was missed. And then I plan on Cerakoting the cases to protect them. I'm going to do clear to show off the cases, and then do another undecided color for the remaining parts to accent the billet cases. Then I need to put it together, go through the rest of the bike and grease everything, break it in, get it tuned for the first combination of parts installed, and get on with testing. I do plan on building a dyno as well to get some quantitative results, which will be another thing to stay tuned for. And aside from this, I want to hear what you guys are most interested in seeing moving forward. Are most of you interested in the build process, the testing process, or just seeing it running and ridden? These are all questions that can help me help you guys, because at the end of the day, I did this for myself, but I also think it's pretty cool, and people are going to want to see it. So the more I can do to show it off in a way that you guys like, the more I will try to do. You're interested in more short, entertaining videos, or longer, more informational ones like this, or a combination of the two. At the end of the day, I'm an engineer. I'm not a YouTuber, so please bear with me as I get started, and help me grow this project into something that's more than just a one-off sick bike. It's been an incredible journey so far, and it's just getting started, honestly. So be sure to like, follow, subscribe, comment, do all that other stuff that'll keep you updated on my progress. And thank you so much for watching. I look forward to seeing you guys again soon.